All right. So, hello and welcome everyone to the eighth week of interactive live sessions for the course on computational fluid dynamics for incompressible flows. This course, as you know, it's being offered by NPTEL, is being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm a PhD scholar at IIT Madras and I'm the TA for this course. And like every other week, we shall be solving some problems together. So let's dig in. So this week, our discussion has been on the stream function vorticity formulation and how to use it to solve for uh, flow fields. So this is a very simple first question, which is asking us what is the primary purpose, the main goal of using stream function vorticity formulation in CFD? Is it to option A, to simplify the Navier-Stokes equations? Is it option B, to improve numerical stability? Is it option C, to conserve mass and momentum? Or is it option D, to reduce the computational time? So read the options carefully. It's a simple question. And once you've figured out the solution, you can either type it in the chat box or you can unmute and answer as well, whichever way you feel comfortable. We already have a quick response in favor of option A. Let's see what others have to say. So the primary goal of using stream function vorticity formulation. Okay. So we've got two responses in favor of option A. Let's take a look at the solution. It is indeed option A, to simplify the Navier-Stokes equations. So as it turns out, in 2D, we have in the primitive formulation of Navier-Stokes equations, three variables, the two velocity components u and v, and the pressure P. And in general, this is our equation. So we have u dou x plus v u dou y equals minus dou p dou x. There will be a 1 by rho here and plus mu into, uh, uh, yeah, mu into the second derivative of u with respect to x and y. I have some doubts. When can I ask? Let's go through the questions. I have some very simple questions today. Once we are done, then you can ask your question. Then the second one, we have u dou v dou x plus v dou y equals minus 1 by rho dou p dou y plus nu into similarly dou 2 v dou x2. There will be a 2 here. And dou 2 v dou y2. And I forgot there's the continuity equation which has to be satisfied as well, which for incompressible flows is given by dou u dou x and dou v dou y equals 0. So we basically have three equations and three unknowns, three variables that we're trying to solve. Now in stream function vorticity formulation, we simplify this down into just two equations in two unknowns. The two unknowns being uh, psi, the stream function, and the vorticity omega. And we have two equations here, so I'll write those down. So the first equation is the Laplacian dou 2 psi dou x2 plus dou 2 psi dou y2 equals minus omega. And the this is the equation to solve for the stream function. And the equation to solve for omega is simply the vorticity transport equation, which is, if you look at the convective side, it's so the transport equation is very similar to the momentum transport equations in the Navier-Stokes equation. So the format is similar. U dou omega dou x plus v dou omega dou y will be equal to nu into dou 2 omega dou x2 plus dou 2 omega dou y2. So you can see that from three equations and three unknowns, so you can go down to two equations and two unknowns. So this simplifies our whole set of equations to solve, basically. And this is the primary goal of using stream function velocity formulation. Okay, so this was a very simple question. We'll move along to the next one. This question number 2 is asking us that in the context of stream function vorticity formulation, what does constant stream function physically mean, physically represent? Is it option A, the velocity components of the fluid flow? Is it option B, the rate of change of vorticity in the fluid flow? Is it option C, the streamline patterns of the fluid flow? Or is it option D, the density distribution within the fluid? Once again, if it's a fluid flow. So it's all about the flow field. Okay, so we have one response in favor of option A, the velocity components of the fluid flow. The question is that in the context of stream function vorticity formulation, what does constant stream function physically represent? Is it the velocity components of the fluid flow? Is it the rate of change of vorticity in the fluid flow? Is it option C, the streamline patterns of the fluid flow? Or is it option D, the density distribution within the fluid flow? Or flow field, rather, whatever you call it. Okay, we have got two responses in favor of option C. Let's take a look at the solution. It is indeed option C. Good. So basically, constant stream functions basically represent the streamlines of the fluid flow. So that's the definition of streamline. So in case, so a very simple example. So if you have a pipe flow like this, but I also give the idea of it does. I mean, they are all related, but the main keyword here is that constant stream function. So in this case, you'll have a flow field like this, a parabolic velocity profile, but the flow is all parallel. So all the constant streamlines would be parallel to the x-axis. So there will be like psi equal to some constant C1, another constant C2, another constant C3 like this. Now this is a very simple case. There could be more complicated cases. Let's say if I have a T junction like this, with flow coming in through this end and going out through these two. In that case, my stream functions would be a bit more complicated. There will be a stagnation point here. In between, there will be. Once again, these lines are of constant stream function, and this sort of gives you the flow pattern, gives you an idea of the flow pattern. Okay. And yes, they are related to the velocity, they are related to the vorticity as well because they're connected. Density distribution doesn't really matter here because we are only dealing with incompressible flows. Another important thing is um, if we are drawing stream functions at so let's take this example for consideration. So if C1, C2, C3, if they're equidistantly spaced, that is meaning C1 minus C2 equal to C2 minus C3, and so on. So in case you make the differences between those constants uh, constant, if you hold that fixed, so let's say delta C is your fixed difference between two streamlines. In that case, if you get very densely packed streamlines like this versus very sparsely packed streamlines elsewhere, it means that the velocity here, let's call it u1, versus the velocity here u2, which one do you think will be greater? between U1 and U2. This is under the condition that I am drawing streamlines at constant width apart. So U1 would be higher. Correct. So in regions of high velocity, the streamlines will be tightly packed to each other, whereas in lower velocity regions, they will be more sparsely spaced. So in this way, if you look at a flow field in which you have plotted the streamlines in such a strategy where the differences are constant, it's the packing density of the streamlines that gives you an idea where there is high velocity and where there is lower velocity. So these are, ways to analyze the flow field visually. It's a good technique. Anyway, so once again, we'll move on to question number 3, which is asking us in the stream function vorticity formulation, what does the vorticity represent? The vorticity omega. Is it option A, the rate of change of velocity? Is it option B, the curl of the velocity field? Is it option C, the divergence of the velocity field? Or is it option D, the magnitude of the velocity field? So, written in mathematical form, the rate of change would be something like dou u dou t, or this is just temporal. It could be, the absolute rate of change as well, which takes into account the spatial change as well. Then we have the curl of the velocity field, which is a mathematical operation, a vector operation on the velocity field. Then you could have the divergence of the velocity field, which is again a vector operation. Then we could have the magnitude of the velocity field, which is this. So you have u v w, then you simply take the magnitude of it, like u square plus v square and square root of it. Anyway. All right, so we have got two quick responses, both in favor of option C, telling that it's the curl of the velocity field. Let's take a look at the actual solution. It is indeed the curl of the velocity field. So this is one way in which, or this is basically the definition of vorticity, that is the curl of the velocity field. So in 3 dimensions, this is what it would look like. We'll have the three unit vectors I, j, k, then, sorry, not dou dou x, dou dou y, dou dou z of the three velocity components, u, v, and w. Okay, I should make a distinction between w and omega clearly. So in 2D, we only have one component, that is the omega z, which we simply call omega. We drop the z, and it becomes dou v dou x minus dou u dou y. So it's the curl of the velocity field. So whichever way so in whichever region I have a high rotation of the velocity field, or high curvature of the velocity field, there I will get high values of omega. This is the a similar concept. So in electromagnetism, we learn about curl a little bit. So the induced magnetic field when a current is flowing depends on the curl of the uh, electric field, whereas the opposite way around as well. That when there's a magnetic field, its curl is proportional to the induced electric currents. So anyway, those are off topic, but yeah. The vorticity represents the curl of the velocity field. it gives you the information of where there will be high rotation and in which regions there will be low rotation. So taking into account one of our earlier examples of the T. So here, the velocity field will be somewhat sort of like this, right? So in these regions where, you can see that the flow is taking a sharp turn, it's rotating like this. In these regions, if you let's say if you took the same thing and plotted a contour of the omega, you will see that in these regions there will be a high value of vorticity. Whereas in regions where there is relatively straight flow, the values of omega would be much lower. So this is once again a way to visually analyze a flow field. Okay, let's move along. We'll move on to question number 4 now, which is asking us what is the mathematical equation? So we have four options here. What is the math? So basically, each option is one equation. Basically, there are two equations each. So what is what can I say, correct set of mathematical equations that relates the stream function to the velocity field in a 2D flow? Is it option A, u equal to dou psi dou y, v equal to minus dou psi dou x? Is it option B, u equal to dou psi dou x, v equal to minus dou psi dou y? Is it option C, u equal to dou v dou y and v equal to minus dou u dou x? Is it option D, u equal to dou u dou x and v equal to minus dou u dou y? We have got one response in favor of option A. Let's see what others have to say. Okay, we've got another response in favor of option B. Let's take a look at the correct answer. It's actually option A. So u equal to dou psi dou y and v equal to minus dou psi dou x is one correct way to relate u and v. There could be another way as well where you flip the convention of the plus and minus sign, where you can say that u is actually minus dou psi dou y and v is plus dou psi dou x. This is also correct. It just depends on the convention that you're following. And you have to make sure that you stick to the same convention throughout and you do not switch between them during your process. But yeah, both are equally acceptable. So the main idea of, if you remember the mechanism, the main uh, philosophy behind this, it will be easier to remember. So stream function is kind of like what is the volume flow rate through a given area, or in 2D it will be a line. So basically, if you take one point and you move a certain distance delta y above it, now, and you have, let's say, velocity u coming in over here. Since delta y is very small, u is the same all across. You can assume that. So it's like differential calculus. So what would be the flow rate through this? The differential flow rate. The differential flow rate will be u into delta y, right? So this is how you get dou psi dou y equals u. Similarly, I'll draw this here. Similarly, let's say you had a point like this and you moved delta x to one side and you had v coming in over here as the velocity. So once again, what will be the flow rate through this differential flow rate? That will be okay. Wait, there is delta y that way, delta x this way. Hmm. Hmm, hmm, hmm. I'm taking the directions correct, right? If v is in this direction, ah, since there is another convention that I'm forgetting. So basically, mm, you go up delta y, you go this way delta x. Yeah, the negative sign. That's what. So there's a specific reason why that negative sign comes. So dou psi increasing in the x direction. Anyway, I forgot this. Next class, I'll try to do this. So there's a specific reason why this happens. I apologize. Yeah. Then if you know, can you help us? Okay. If dou psi increases in the y direction, that means u is positive, and if it decreases in the x direction, that means there's a positive Q. Q function is defined as the negative derivative of it in tangential direction given velocity of flow in that direction. Stream function is defined as the negative derivative of it in the tangential direction given velocity of flow in that direction. So if I have, a stream function like this is the tangential direction at this point. So how does that give us the negative sign? Anyway, I can't figure this out. Let's not waste much time here. Uh, I'll refresh the thing and then we'll discuss this next step. Let's move on for now. We'll move on to question number 5, which is asking us how is the vorticity calculated in the stream function vorticity formulation? There are four options. That is through taking the gradient of the stream function, by taking the curl of the velocity field, by taking the divergence of the velocity field, or by taking the Laplacian of the stream function. The main keyword here is how is vorticity calculated in the stream function vorticity formulation. Okay, we have two quick responses, both in favor of option D. Let's take a look at the solution. It is indeed option D. So basically, omega is the negative of the Laplacian of the stream function. Uh, if I expand it, it's nothing but dou 2 psi dou x squared plus dou 2 psi dou y squared. Yeah, you discretize both of these derivatives and you find out what omega is. Good. So one common pitfall here is that many people say that it's by taking the curl of the velocity field, but we don't have the velocity field in the first place. We are trying to solve for it, and we solve for it in the two variables, the stream function and the vorticity. So we have to play within those two only. All right. So let's move on to the next question, question number 6, which is asking us how does the stream function vorticity formulation handle boundary conditions? Is it option A that it automatically satisfies all boundary conditions? Is it option B? It requires additional boundary conditions beyond those for the velocity field. Is it option C? It does not require any boundary conditions. Or is it option D? It only requires boundary conditions for the vorticity field. There is no option. So maybe option E. What would you suggest option E should be? It requires velocity conditions mostly. Okay. Okay. Let's hear what others have to say. Yes, you are right. You're not wrong. You actually told the correct answer. So can you find something within the four options available here? It must satisfy Dirichlet boundary. It's not required. I mean, it could be Neumann boundary condition as well. Doesn't matter. It doesn't have to be Dirichlet. D maybe. So it only requires boundary conditions for the vorticity field and not for the stream function. Uh, Shivank has actually given the right answer in his chat box, but okay, let's take a look at the solution. It might be, the language might be a bit confusing. So it's option B that it requires additional boundary conditions beyond those for the velocity field, and it can be obtained from the velocity boundary conditions. Basically, you start off with the velocity boundary conditions, as you already told. Now you can derive boundary conditions for both stream function as well as vorticity, and those are required. It's not that they are not required. Both are required. but you can derive them from the velocity boundary conditions if they are known. In case you have a setup where you are, directly given that, this should be the stream function boundary condition, this should be the vorticity condition, then well and good. You take that and start using it. If not, if you have the velocity boundary conditions, then you can derive them from there, as was shown in the lectures. There was, multiple examples taken. So you need boundary conditions in psi in omega. Where do you get them from? Doesn't matter. It could be through the velocity boundary conditions or directly as well. All right, let's keep moving. Let's move on to question number 7. How is pressure calculated in stream function vorticity formulation? Is it by option A, by using Bernoulli's equation? Is it option B, by using pressure Poisson equation? Is it option C, by using Euler's equation? Or is it option D, pressure cannot be calculated in stream function vorticity formulation? Stream function vorticity equation, whatever. Okay, we have two quick responses in favor of option D. The pressure cannot be calculated, even if I needed it. Let's take a look at the solution. It's actually by using pressure Poisson equation. So let's say you have found the solution for omega and psi. Then you are asked to calculate the pressure. It's not that you can't calculate, there is a way. So basically, you start off with the Navier-Stokes equation. This was discussed in one of the lectures. So basically, you start off with the Navier-Stokes equations, and questions are very confusing. Sorry, man. So you go back to the lectures. Pressure can be calculated using stream function vorticity formulation, and it can be calculated by using the pressure Poisson equation, which looks sort of like this. So basically, you have the Laplacian of pressure on the left-hand side. That is not the goal of the equation. What if the goal is to find the pressure? If you need the pressure distribution, what will you do? You'll just simply say that I cannot do it using stream function vorticity. Yeah, yeah, I'm trying to write it. Might be wrong. Let me check it once. Square. I think it should be square individually. Check that once. It was in lecture 3, probably. Ah, it's the other way around. So negative of this. Anyway, so the way that you get this, let me tell you that, so it will be easier to remember. So basically, you have the Navier-Stokes equations, right? Dou u dou y equals -1 by rho. Let's keep rho in this side. Minus rho p dou x plus nu, Laplacian of u. Then you have u dou v dou x plus v dou v dou y equals minus. Okay, if I take rho, then it will be mu, not nu. Sorry. Yeah, so this is what you have, right? Let's call these equations 1 and equation 2. Now, the way to get the vorticity equation is that you take the goal there is to eliminate the pressure out of these two equations. So over there, what you do is you take dodo y of equation 1 and you subtract it from dodo x of equation 2. That gives you the omega equation. And you can imagine, let's focus on these terms. So I took y derivative of this and I took x derivative of this. So both gave me dou 2p, the mixed derivative, right? You can see that what's happening here. So you simply eliminate these two and you get the omega equation. And the way you get the pressure Poisson equation is that you do the opposite. For getting the pressure Poisson equation, what you do is you take the x derivative of equation 1 and you add it to the y derivative of equation 2. So here you can see the first one. This one gets derived by x, this one gets derived by y. So that gives me the Laplacian of p. And rest of the things are in u and v. I can cast them in the form of gradients of psi, and then that will give me some function of psi. And this is what that function of psi is. So given I know the solution, what the stream function is, then I can use this equation to calculate the pressure. And I need to calculate this only once. It's not that I have to iteratively solve this like what I did to get to the solution. I already have the solution. I simply manipulate it once to get what the pressure distribution is. So it's not that we cannot know what the pressure is. There is a way to get there. Any questions on this?
So it's actually a very long process to find the pressure.
Yeah, but let's say in while doing the simulation, while you're trying to calculate the solution of psi and omega, you did that iteration maybe thousands and hundreds and thousands of times. But for calculating the pressure, you only need to do it once when you already have the solution. What's the other alternative? The other alternative is to solve for the Navier-Stokes equations in their primitive form, where you had three equations and three unknowns. Whereas in this one, the majority of the computations where you're doing thousands of iterations, you only have two equations and two unknowns. So overall, it becomes much simpler, right? Do you do you agree or not?
Yes, sir, agree.
Hmm. Okay. So let's move on. Move on to question number 8, which is asking us, can the stream function vorticity formulation be used for three-dimensional flow fields? Is it option A? So we have got options A and B telling us yes with some caveat, and C and D telling us no with some reason. So it's not just use yes and no. There's some additional facts you have to consider. So option A is yes, but it requires the use of vector calculus to formulate the equations. We already have one response in favor of this. Option B says yes. It is a general formulation that can be used for both two-dimensional and three-dimensional flows. Option C says no. It is only valid for certain types of flow fields, such as laminar or steady-state flows. And option D says no. It can only be used for two-dimensional flow fields. Okay, let's simplify this down. I mean, forget the reason. If it was a yes or no question, what would you choose? Let's say no. Yes. Okay. Let's take a look at the solution then. The correct answer is yes, but it requires the use of vector calculus. So it becomes insanely more complicated when we go to 3D. So in 2D, we already saw the relationships between UV and psi omega, right? So these four things were correlated to related to each other in pretty simple ways. Now, and so yeah, so few things. In 2D, you have only one component of psi. Psi is just a constant number at each point. Same for omega. So in case of a 2D flow field, you don't really need to worry about omega x and omega y. So let's say if your 2D plane is xy, it's only omega z component that you are worried about. That's the only thing that exists. Now, once we go to 3D, I have three components of psi. It becomes a vector basically. So in other words, the vector psi is equal to some psi x I cap plus psi y j cap plus psi j k cap. Similarly, omega also is a three-dimensional vector now in which you cannot ignore two components and only consider one. So this is also omega x I cap plus omega y j cap plus some omega z k cap. Now, how many unknowns do you have? So here in 2D, as we went from the Navier-Stokes to stream function vorticity, we went from three equations and three variables down to two equations, two variables, right? In 3D, for 3D Navier-Stokes, how many equations and unknowns do you have? You simply have U, V, W, and P, right? So four unknowns, as well as four equations: the continuity equation and the three momentum equations: x momentum, y momentum, z momentum. So now we're Stokes. You have four equations and four unknowns. Now in this 3D, when you go to stream function vorticity formulation, how many unknowns do you have? Take a look at this. How many unknowns? So all the three components are unknowns, right? For both psi and omega. So you have six unknowns and you will need six equations as well. You can get six equations, and for that, a terrible amount of vector calculus is needed. But at the end of the day, there is no point in doing that because you're complicating your whole thing. The first question, if you remember, what is the main purpose of using the stream function vorticity formulation? To simplify it, to go from three variables to to two variables. Here it is complicating more. So going from four to six. So it makes the whole thing really messy. You can do it if you want, but there's no real benefit to it. Okay. Actually, I'm thinking when we simultaneously solve it, number of unknown may decrease. See, the moment you're telling you're simultaneously solving, you are simultaneously solving for multiple variables. Yeah, but it's good that you're thinking, like try to come up with something. It might be interesting. In some weeks videos, there are some codes in C given, so we have to learn the program too. Not really, not really. You can learn any program and try to implement these. The C program was, you know, you don't need to learn C programming as such, but make sure that you understand the algorithm that is going on there. That, omega ij, you're looping from I equal to 2 to some n minus 1, those things. Stream function and vorticity all are here. Yes, everything is related, but most of it is unknown. You have to solve for it. That's the main catch there. Can you open question 6? Yes. Let's go back. How does this one? Is explained? Okay. So basically, let's take the pipe flow example once again, the equate flow between two parallel plates. So basically, you have what are the boundary conditions for this rectangular domain? So for these two walls, it's simply U equals V equals 0, right? No slip and no penetration boundary condition. And for this inlet, I have U equal to some constant U naught, a constant velocity coming in. And I assume that, this whole thing is long enough so that the flow gets fully developed and there is no development in the outflow region. So in outflow, basically, I say that dou U dou X equals dou V dou X. So nothing is changing in the X direction. Now, this is so if I'm trying to use stream function vorticity formulation, knowing these U's are not enough. I have to find out what the stream function and vorticity boundary conditions are as well. So let's take one example. So let's take for this wall, I know that U equal to 0. So that must mean that uh, dou psi dou y is also 0, as well as V is 0, which means minus dou psi dou x is also 0. So for this wall meaning that, dou y is constant, I only move in x. So here psi should be some constant. Same thing for this one as well, psi equal to some constant. Similarly, you can find what should be the omega at that wall as well. So let's go through all the questions then you can. So omega is given by dou psi dou x square plus dou psi dou y square. And since dou psi dou x is 0, its second derivative should also be 0. And this one is also 0. So basically omega is also 0 for this wall, right? So similarly, from the velocity information, you find out what the psi and omega would be at the boundaries. Those boundary conditions are needed for solving. Okay. All right. So we went till this far. Okay. Two more questions remaining. The question number 9 is asking us which dimensionless number appears in the non-dimensionalized form of the stream function vorticity equations? Is it option A, Prandtl number, PR, the Courant number, CO, Struhal number, ST, or is it the Reynolds number, RE? So far, we looked at the dimensional form of the stream function vorticity equation. If we non-dimensionalize it, which dimensionless group shows up? C, maybe. Struhal number. Okay, let's see what others have to say. D. Okay. Let's take a look at the solution. It is option D, Reynolds number. So basically, you take the original form of the stream function vorticity equations and you non-dimensionalize them. So you say that my, okay, not you. Here I have psi and omega. So you tell that your non-dimensional psi is your dimensional psi divided by u into L, and u and L are the characteristic velocity and characteristic length of the system. And you say omega star is your omega divided by u over L. And you uh, replace all the psi's and omegas in your equations with the psi star and omega star. Then you should get something like this. So this equation remains intact. Okay, and these are also important. So your x star is x over L, and y star is also y over L. This one remains the same, but the vorticity equation now has an 1 over RE of the Laplacian, but the Laplacian now is in terms of x star and y star. So Reynolds number is what shows up, and Reynolds number is nothing but rho u L over E. Okay, it's a simple exercise. You can try doing it. This is what we'll get. Okay, moving on to the last question of today's session. It's a simple true or false question, which is asking us that for two-dimensional incompressible flows, vorticity stream function formulation is more accurate than velocity pressure formulations. Is it true or false? Given that you use the same numerical scheme and everything else. May be true. Why? Why do you think so?
Because we have derived in the previous question the pressure equation from the vorticity.
That we can do, but why do you think it should be more accurate suddenly?
I have just guessed the answer.
Okay, no problem. Oh, okay, let's take a look at the solution. It is actually true. The reason is very interesting. So let's say you use the central difference scheme for your stream function vorticity formulation, and all the discretizations that you did, they were order delta x squared, y squared, whatever. Okay, so you know your psi in second order accuracy. Now, what is psi actually? U and V can be related to dou psi, dou x, dou psi, dou y, right? Sorry, not x. Dou psi, dou y. Now, you know the gradient of this psi in delta x squared. So let's for a minute let's think that u delta x and delta y are interchangeable, or we can do it the other way around as well. Let's say v equal to minus dou psi dou x. So you know the gradient of this in terms of the second order. So that means your velocity v, you will know that in third order, right? You get the point, right? So you know the gradients of a number in some sort of accuracy. So when you're trying to find out the velocities, oh, sorry, uh, my bad. Oh, yeah, this is why that thing happened. The shy, you know, in some order of accuracy. So you're now doing a gradient of that. You're again dividing it by some delta x, and that gives you v in an higher order of accuracy. So if it's 2, it becomes 3. If it is n, then it becomes at least n plus 1. So the velocities, you can get one added order of accuracy if you are solving the stream function vorticity formulation. Okay, so my questions have ended. If you
Sir, I
have any
have
questions,
yes,
yeah,
sir, I have doubt. Sir, in
yeah. Mm,
week 8
mm,
assignment, I have
mm,
doubt. There's a
mm,
question number 3, the discretized equation at the top of the wall. A square is given,
mm,
and on every wall, u equal to 0 and v equal to 0 is given.
mm. Then,
There is a square.
mm.
Let's make the please sir make the square.
No, see, technically, I cannot help you with question assignment 8 questions today. You can ask them in the next week.
Sir, I didn't get the clue to solve this type of question.
You, you
Although
tell if you tell
sir
me the
has not.
question, I'll give you a clue, but I can't, help you solve it right now. So there's a square and the velocity boundary conditions are given, as I understand.
Yes, sir.
What else do you have to do?
Yes, sir. And we have to take the like correct equation like omega I comma n equals to minus 2 by delta's x square, like something is given.
Hmm. So where is your problem here?
So my problem is, sir didn't solve this type of question in the video lecture, and I
Okay,
didn't find any clue to
uh,
solve.
okay, you give it a shot. We'll discuss this in detail next week. Right now, I cannot do it. I'm sorry.
Now I can ask.
Yeah, let's see if he has anything else. Shovanshu, do you have anything else other than this one?
No, sir.
Okay.
Thank God, it takes more than an hour to ask a note. So, uh, so basically, the first question is like about the periodic boundary condition. What does periodic boundary condition means? Because like it was told that it is the primary condition to follow the that
So,
procedure.
so basically, periodic boundary condition says that, this point, x equal to 0 and x equal to L, they are connected. So as if you take this string and you connect them and you make it something like this. This is your x equal to 0. This is your x equal to L. So mathematically, you will write that u equals 0 equals u at L. Or in the index notation, it would be u1, that is ui equal to 1, should be equal to un, I equal to n. This is for u, it could be anything v, w, z, t. So
Yeah,
you
but
make the
how?
domain periodic.
Okay, but how does it help to like for why it is a necessary condition for stability analysis?
Not
Like one.
necessary, it depends on the scenario. So it's usually used in waves and things like that. So it just makes your whole domain sort of loop around it. Infinite, you make it infinite using a, technically which is finite. You simulate the effects of what would have been if this was a infinite domain.
Actually, this point is written like the limitations of von Neumann stability analysis. In that,
Mm,
it was told that first of all, it should be linear PD.
mm, mm,
Second, it has constant coefficient, and the third one
mm.
is it has periodic boundary
Yeah,
conditions.
yeah.
So the
So.
effects of boundary
Mm.
condition is not considered. What does like effect is not considered?
Yeah, so basically, if you have fixed Dirichlet or Neumann boundary conditions, it might mess with the Fourier series assumption that we do with the errors in von Neumann stability analysis.
Okay, but if we
So,
have this periodic thing, then it will not do that.
periodic basically means you have it infinitely long. So you can have a Fourier series infinitely long, a sine wave or cos wave that is infinite in both directions. That's why.
Okay, and that condition of infinite will be fulfilled if initial and the final thing is same, like u0 is equals to uf.
Yeah, yeah, yeah.
Like how, like can you like that how this like some mathematics behind it, like how this infinite condition is fulfilled if I consider u0 is equals to
Yeah,
uf.
simply this. You took this finite thing and you connected both ends. So now, whichever way you're going, so let's say if you have a wave like this that is moving in this way, so it will come here, sorry. So it will come here, then here it will end here and it will start peaking from this end. So there was a mobile game Snake in the older
Yeah.
mobile phones, if you remember that. So if the snake goes in through one of the boundaries, it comes out through the other. So that
Yeah.
was periodic boundary condition in play.
Yeah, understand, understand now
Yeah.
also. But if we put any like definitely our solution will get affected by the boundary conditions.
Yeah,
So,
this is how it gets affected.
but how it will not affect the solution? Like
It will affect the solution. This is how it will affect the solution. This is the
no, no,
solution that you
but
get for.
the
So
stability analysis will not get affected. That is what I'm saying. That
no, yeah. So the thing is, in for von Neumann stability analysis to be done, we have to make this assumption. Now, the in a real scenario, you might not have periodic boundary conditions, right? Yet you
yeah.
say that, okay, von Neumann stability analysis has told me that this will be unstable. That's why it will be unstable. So it gives you a clue. But that
Uh,
is not a strict condition for application of it. It's just strict for deriving it.
no, no. I'm saying like by changing the boundary conditions,
Hmm.
our solution will change,
Yeah,
but the stability criteria remains same,
yeah,
right?
yeah.
Okay. So by considering this as a periodic boundary condition,
Hmm.
we are getting this thing that it is becoming independent of boundary conditions.
Sort of, yeah.
Okay. But like I cannot
See the
like prove
the
it
app, yeah,
mathematically. Like
yeah. Let me try to clarify this. So the stability analysis when you do, then you assume that there is a periodic boundary condition, and
mm,
that gives you a result. And what you do with that result is that you say that if I use the same scheme for a different scenario, which may or may not have periodic boundary condition, then also you apply the same result that, okay, this has told me it will be unstable, so this will be unstable. This has told me it will be stable,
No, no,
so
no.
this
The
will be
second
unstable.
case is like
Thing.
boundary condition is different. Condition
Different.
is periodic itself, but
It's
boundary condition
different.
is
It's different. Yet you say that the stability is the same as what it would have been if it was periodic.
okay.
So this is, a jump that we make in logic.
Acha, okay, okay. And the second thing is like M in that expression. If you can open the first lecture of seventh week
First lecture of seventh week. Okay, I'll stop sharing.
notes. Yeah.
Hello, sir.
Yeah.
Sir, I was telling that, sir, after the last lecture that we got in the month of April,
Hmm.
the week 12.
Hmm.
So, can you please conduct some other, actually, the doubt classes
Yeah,
for
so there,
solving,
yeah,
actually,
yeah.
for at least one or two?
So after week 12, there will be a week 13 meeting as well, when we will discuss doubts and, I will prepare some questions from the whole lecture series, like starting from week 1 to week 12. And you can ask doubts then as well.
Yes, sir, at least
Mm.
plan two,
Yeah, yeah. No,
because
week
everybody
13.
is asking the doubt, and
Mm.
for one person, it is not enough to ask too much doubt in that session. Means everyone has to ask their own doubts.
Yeah, yeah. So week 13 will be there. So, okay. Which lecture? Week 7,
First lecture.
first lecture. Okay, this is the video.
If
Okay.
you have like notes, then it would be helpful.
Yeah, yeah.
Just yeah. So second, third, next slide. Okay, next. Yeah, in this also, or maybe in the next slide, maybe next. Yeah, here like this m goes from minus n to n, right? So like what I'm trying to understand is that like m is the number of total number of nodes in the
Mm,
domain,
mm,
right?
yeah, yeah.
So uh, the total number of waves that
Mm,
we are going to consider
mm.
are equal to number of nodes.
They are actually it should be one less because for the smallest one you need two nodes, and for the
Hmm.
biggest one you need all the nodes. So it should go
Yeah,
from
but
two.
here we are going from minus n to n, and minus n is the last point, and from minus n to n.
Uh, these may not be harmonics. I don't know. Error is a superposition of harmonic errors, whatever number. Yeah, I'm not sure. I think I believe it should go from 2 to 2n. in this case.
Mm, okay.
I mean, the total number of harmonics that we are adding, that should
Or I
be n
think
minus
like,
one.
yeah, yeah, but one
Mm,
one I think that one you saying it should be one less. I think
mm.
that maybe the constant term, like
I
we
don't know.
start the series from the
Yeah,
constant
yeah,
a naught.
yeah. I get that, but I don't think these are related. One thing could be that here it's not the harmonics that is being added, it's the individual points.
No,
Could
it's a
be.
harmonic
I'm not
only,
sure.
like KMPEI, like the equation itself is a harmonic.
Yeah, I'm not sure. Sorry.
Okay, can you like find it like this, if it is
Yeah, okay.
possible?
I'll ask Professor. Yeah.
Yeah, yeah.
Mm,
Okay, and the next thing about in the next slide. Okay, now this slide itself is very confusing because I think I have asked you about this thing.
mm,
So I understand that one thing is like practically we find out that amplification factor is going to change
mm,
exponentially.
mm.
So exponentially, so if I just start from the very basic, I will say it is something e raised to the power t,
Okay.
right?
E raised to the power something into t. Yeah.
Something, okay, yeah,
Mm,
something into t.
mm.
But why should I take this z raised to the power n?
Oh,
I mean,
okay. Yeah, yeah. So basically, E into, let's say you call it, so over here only it is there. So U equal to A n delta t. So T you divide into n into delta t. So starting from 0, you're getting delta t, 2 delta t, 3 delta t, 4 delta t, n delta t. Okay.
okay,
So in
oh
each
yeah,
so in each step you are multiplying e to the power delta t to this.
yeah,
Mm.
like,
So that's what exponential series is, that you keep multiplying it with
but by
something.
how much term is depend upon the time step?
Yeah, basically z equal to e power a delta t. That's the thing. So each time you move to the next time step, you get multiplied by e power a delta t.
Okay,
So that
actually,
is why you can write this as z power n, that each time step I'm getting multiplied by z.
oh, okay. Each time I'm multiplying by z factor,
Mhm.
and every
Yeah.
time I increase by e raised to power at.
Mhm. So basically, see, the main thing is exponential growth and multiplicative growth. They are the same thing.
Yeah, and it take care of obviously the complex thing also, like if it oscillate.
Yeah, yeah.
Yeah, okay. Okay, I'll look into it because the assumption that how amplification factor is like mathematically how we like encapsulate this thing in the equation, that is
Mm.
like I'm looking into those things.
Okay.
Okay. Yeah. So next is like it was told that we understand that amplification factor should be less than one. Means it should not
Mm.
grow.
Mm.
But at the same time, it was told that it is okay that if it is only bounded. My doubt is like if
No,
it is bounded, how
no,
does
no,
it
no.
help? Like every
No, no,
time it
it
is going
should,
to,
yeah, it should decay.
it
Bounded
should
is not
decay.
enough. Yeah, it should be less
Actually,
than one. Yeah.
yeah, because at one point professor has told that it should either decay or remain bounded at least.
Okay. See,
That
remaining in things that move exponentially with time, remaining bounded is the same as telling that it does not blow up,
grow.
it decays. So
No,
those
bounded.
two,
Bounded it also consider the fact that it may remain same.
yeah, but it cannot remain same because it's getting multiplied by the same thing again and again, right? So remaining bounded means that it decays. So see, there is no option of staying same. It could either go up or go down. So remaining bounded means that it goes down.
It
Maybe
goes.
that way. Yeah.
Yeah, yeah, yeah. Okay. Now in the next lecture, week two, sorry, week lecture two of weeks, in the lecture
Mm.
two,
Hmm.
in this Richardson method. Next,
Larson and
yeah,
Richardson. Yeah.
here, next slide. Yeah, here we got two G,
Mm.
two amplification factor.
Yeah.
One, one we are sure that it is going to be
Mm.
greater than one,
Mm.
but other can be less than zero.
Yeah.
Other can be less than
Less
one.
than one. Yeah.
Yeah, but then we cannot. How we can say that it is unconditionally unstable? At least,
Because this one that we are sure that is greater than one, that itself will blow the errors up because both exist. It's not like either one of them exists.
oh, okay, okay, okay. Now
Mm.
I understand. Like each time, this
Mm.
growing term will keep on increasing,
Yeah.
and one term might be decreasing,
The
but the
the
next term.
other one may not come into the picture. I mean, the effects of the other one may not be significant, but this one will make sure that it blows up.
Yeah, 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 yeah. Now I understand. Thank you. Now in next lecture, seventh,
Mm.
third lecture.
Yeah.
Yeah. In this Eilers FTFS, yeah, yeah. Here,
Mm.
like it is directly very easy to say that like G is less than zero. In the complex term, we usually definitely say that mod G square should be less than zero.
Mm.
Like graphically, we can see that it should be
Mm.
inside the circle.
Mm.
But I cannot like directly visualize this thing that how it helped to decay the error. Like mod of amplification square is less than one.
Okay. So, how do I explain this?
Like I might be weak in some complex
Y-
numbers, so that's why.
Yeah, complex numbers are confusing. Mm, See, if we consider only the real part, then it's easy to visualize.
Yeah,
But the combined effect of imaginary and real, that might be a bit difficult.
yeah. Only thing is that graphically we can see that it
Hmm.
make a circle and inside it should be there.
No, in fact, graphically itself, it's more difficult. Mathematically, it's easier. You just find out the magnitude and see if it's less than or greater than one.
Yeah. So like it is difficult to visualize like how amplification factor is keeping it less inside the circle, making it to not to grow.
Hmm. Yeah. But see, think of it as this way, that G is the rate of growth of error. And if the magnitude of G is less than equal to 1, that means I'm safe, that my error decays with time.
Okay. Yeah. Like I can like intuitively say that
Yeah,
okay,
simply.
okay.
Hmm.
And like in the uh, next slide,
Hmm.
next slide, next slide, further next, I guess further, yeah, here. So
BTCS.
here, yeah, 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 this thing. In this, like again,
Hmm.
like it is a
Yeah,
little
so same
math-
logic.
logic is everything same, but
Hmm.
what I'm trying to ask, like this
Hmm.
G square mod of G square, we generally
Hmm.
find like uh, real part square plus imaginary part square.
Hmm.
But if it is reciprocal, then we also
Then
have done the
also,
same.
yeah, then also you can do it. You check that, you can do it.
Yeah, but what I did generally that I take the 1 minus iota
You can
lambda
do it, you
sine
will get
theta.
the yeah, you will get back the same thing. So this is a shortcut.
Okay, it's just a
Hmm.
shortcut because I
Yeah.
usually multiply
Hmm.
numerator and
Yeah,
denominator.
you can
Then we solve it.
try that out. You'll get this only back. But
Okay.
Just for the sake of sanity, you can check it out
Mm. Okay, okay.
by
So the
inverting the
next,
reciprocal line. Yeah,
okay, in the next fourth lecture,
fourth lecture.
just first slide itself, maybe. Yeah, the here doubt is like obviously professor has also already told this that
Hmm,
we first put this first we wrote this equation using Taylor series,
hmm,
and we again put it back in the equation.
So
I
the
don't
you replace the temporal, the time derivatives with the space derivatives again.
no, that is the next thing. The first
Hmm,
thing in the first slide only itself. Keep it on the first slide.
yeah.
Yeah, the first step del phi by del t is equals to 2
Hmm,
c del phi by del x.
hmm,
Here we have written the next line
hmm,
phi I n plus 1 minus phi. This we have written by Taylor series.
hmm,
By eliminating those extra term, we have written this.
yeah.
Now I got this equation using Taylor series,
Hmm.
and then finally again I am writing this, expanding it using Taylor series.
No, second time I'm not expanding using Taylor series. So see, now you have Taylor series in time in the left hand side and Taylor series in x on the right hand side, right?
No, but this equation what we get after that we
Yeah.
expand again with respect to
No,
Taylor, like
the I'm telling you. So in the second step, you replace the time derivatives. See this one, the dou 2 phi dou t2, the third
yeah, here we
derivative
have
with
done,
respect
but
to.
before it
Hmm.
reaching to that level,
Hmm.
we have like I find like first I have written this I del phi by del t is equals to minus c del phi by del x. Okay. Now
Hmm.
next line we have written phi I n plus 1. This we have written all those things
Hmm.
using Taylor series by using
Hmm.
the forward backward scheme,
Hmm.
right?
Hmm. Yeah.
Forward time backward space.
Yeah.
So
Yeah.
here I am already using Taylor series.
Hmm. Hmm.
Now it was written based on it we get this FDE equation which is 1.
Yeah. Hmm.
Now again I use the Taylor series expansion
Yeah.
to expand phi I n minus 1.
Hmm. Hmm. Hmm.
But this phi I n minus 1 comes from the Taylor series itself. So we are,
Yeah. So
and then the
why
third step is, uh,
why are we doing this ugly math? The main thing is we saw that if we solve the thing in this way over here without all these before the second Taylor series expansion. Like if I had the equation dou phi dou t equal to minus c dou phi dou x and I did, you know, FTBS discretization and I solved it, then I already saw that, I get errors like this. Then I'm trying to find out where are these errors coming from. They shouldn't have come. So in that investigation, it turns out that that dou phi dou t equal to minus dou phi dou x should have stopped over there, but there are these higher order terms giving me a few terms which are coming here, which is similar to viscosity terms, where I have the second derivative of phi and the third derivative of phi with respect to
yeah,
x. So the
just. I understand your point,
Hmm,
but my question is why
hmm,
again Taylor series? At the first equation we have written in
hmm.
that equation itself, we have not, if we have not truncated the other
No, but
terms, we
yeah,
will get the
we
same.
we do not get these. We do not get these terms over there, right? So, see, you're missing one important point. That is, in the Taylor series expansion in time, there we are replacing a few temporal derivatives with space derivatives, and then taking uh, those from the right hand side as well as the left hand side combined. So that
No,
finally gives me these terms.
yeah, yeah, I understand. But
Hmm,
at the very
hmm,
first point, I have
hmm.
written after trunk. Can you just move ahead?
Yeah.
Yeah, the
Hmm,
very first
hmm,
equation,
hmm,
that phi I n plus 1
hmm,
phi.
hmm, hmm,
This I have written by eliminating some terms, by truncating those error
hmm,
terms.
hmm, hmm.
If I
Yeah.
have not truncated those terms,
Hmm.
I will get the artificial viscosity right here. Why
Yeah.
should I go again putting
Oh,
Taylor series and
okay.
yeah,
It's just to find it out because here we are ignoring it and then seeing the effects of ignoring it. And in the second way, when we are
Okay.
not ignoring and trying to find out where was the actual error coming in from.
Oh, now I understand. That's
Hmm.
why I think that okay. So at first we have ignored it and see
Hmm.
what are the result, and then the
Hmm.
second we again put it
We
back to
try to
see what
find
we
out
have missed.
exactly where that problem is coming from.
Okay. So if at the so I just make an experiment just
Hmm. Hmm.
like if at the very first if I don't truncate the error
Hmm.
and wrote the equation, I should get the same artificial viscosity as I'm getting after like this.
It depends on where you truncate, like how many terms you are keeping, because
Yeah, but if the truncation like order is same, I
hmm,
must get the same thing.
technically you should. I don't know. Okay, Shubhangshu, bye.
Okay, so means I should get
Yeah, so that is the thing over here.
okay, okay. And the next thing is how we uh, how we find this term. Like Professor has not told. Can you give don't drive, but at least give me some
Hmm.
idea that how we change this term into spatial
Yeah, so
distance.
main funda is this, that my original equation is a very direct linear relationship between derivatives of time and space. So if I need to find the second derivative with respect to space, I just simply take another derivative with respect to time and that gives me that. If I do another derivative with respect to time, I will get another derivative with respect to space. These are directly connected and
Okay, and
linearly.
we are
The
just
main thing is they're linearly connected.
and we
Uh,
directly
l-
putting it here.
yeah, let's see if sir has done that somewhere.
Yeah, here in this slide he has not done it. He just told that
Hmm.
you can
Anyway,
find it.
see, this is the wave equation, right? So the second order wave equation, it's dou 2 phi dou t2 equal to c square dou 2 phi dou x square. How do you get that? By simply deriving it once.
Yeah. Okay, okay. So that's we do. But
Hmm.
in the next slide, in the next
Hmm.
slide, here it was written that we will find
Oh,
up to the order of
yeah,
a
yeah, yeah.
how
This
this
is a bit more complicated. So here it's not just you have to find Dofi Doti 2, but you have to find it with a specific order of accuracy.
hmm,
So this is more complicated. I don't know the exact procedure.
yeah, that is also okay. So this is the second thing. If you can find at least some source where I can see like, how we can do
Mm-hmm.
that.
Yeah.
Yeah,
Might be in some advanced CFD book.
yeah. And
See, only these first terms that you can find by directly repeated derivation. But
yeah,
this second term will be difficult to find. Might be a bit more involved process
hmm,
to find this one. You
yeah.
can see my
Can you?
cursor, right?
Yeah, 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 I can
Yeah,
see.
this one will be a bit tricky to find out.
Yeah. Can you move to the next slide?
Hmm.
Yeah, wait. Here, this factor 2 in
Hmm.
this equation, 2 lambda square,
Hmm.
this is not coming. If you see in the previous slide, it should be 3. Like here itself, if you
It's
see,
coming
see
from here, probably this
yeah,
term.
and in the previous, in this just here, in rearrangement, if you see
Hmm.
that if we take c delta x square by 6 common, then I should get 3 so that it cut down and to get this thing. Like if you
Hmm. Okay, yeah, C is in the bottom, and if I take 6 out, is it? No,
yeah.
6 by 6 is taken out, so there are two instances of this happening, I guess. Mhm. This is one that is contributing to the first term.
No, C delta X in cubic, yeah, in cubic we have
Hmm.
taken.
See, this is the first term over here, the one with coefficient 2.
Hmm.
That is basically c cube delta x square. No, there is no delta x square because these will cancel out. This is basically c cube into delta t squared.
Yeah,
That's what you
you
need.
are pointing out at the right thing.
Hmm.
So here I need two in the denominator
Yeah.
after
So
so I
this
should
is
have three
one.
here.
No,
Yeah.
this is one that I'm hovering over,
Hmm.
and this is the other one. So if I'm taking, okay, this one is 1 by 6, this one's 1 by 2, and if I take 1 by 6 common,
Okay,
yeah,
okay, okay.
if I take
Yeah.
1 by 6 common, then this one is negative and this one is 3,
Hmm.
right? So 3 minus 1 gives me 2.
Okay, okay, okay. Yeah, I think I missed one term
Hmm.
while writing. Okay, okay, okay. Uh, how to
So
maintain?
minus 3 plus 1 gives me minus 2, and this is actually minus 2 because there's minus on the outside.
Okay, and this dispersion error and dissipation error, these are just
Hmm.
like we can like this is observation like
Yeah,
that it is Wegel's terms or
yeah,
smearing.
yeah.
This is
Hmm.
just observation, right?
So it was shown in one of these slides as well,
Like
right?
because it was told that if it is even then it will get smears or it will odd
Hmm.
then it will Wegel. So
Hmm.
these are just like observations like
Yeah,
mathematically, or I can
observations. And there is one physical explanation as well. So let's say for the dispersion one, the one that you get when you have um, even terms. That is similar to what would have happened if there was some viscosity, there was some diffusion of the physical thing,
okay.
right? There was no solution shown. I think there was one. Was it in the first lecture?
No, no, in the last lecture, last slide.
No, these are sketches. Wasn't
Only
a
this much
real.
is told. In the previous slide, I think they have just told that this contribute to this thing and this contribute to this
Okay.
thing, dissipation.
Anyway, so you look at this middle one, the green one, dissipation
Hmm.
error. So this happens when there is even terms like dou 2 phi dou x square. And
Oh,
dou 2 phi dou x square, where does it occur? In diffusion terms like heat diffusion, you will find dou 2 t dou x square. In momentum diffusion, in the right hand side of the Navier-Stokes, you will see this mu into dou 2 u dou x square, these kind of terms. So
yeah.
this is what distributes physical quantities down their concentration gradient. So you have high concentration in one place, low concentration in the other place. There will be some diffusion. And that's exactly what happens here. So in that way, you can physically connect that, okay, one unwanted double derivative is coming, which is bringing in an effect which is like viscosity. That's where the term artificial viscosity comes from.
Okay. Okay. Yeah. And
Yeah.
it was told that we have to. Actually, my voice is echoing. Yeah, yeah, we get in the very first lecture at somewhere near 18 minutes, 19 minutes. Yeah, first lecture. Next. Yeah, like here it was told that we have to use like it is told like you have to choose some implicit or explicit scheme. But here we don't have any like time component. So
So for elliptic equations, you had implicit and explicit schemes, right? There was there
okay,
any time component for it?
okay, okay.
Elliptic.
But
These are similar to elliptic.
okay, so we can go in implicit or explicit at our choice. Yeah, but are there any species like there are solvers, implicit solvers and
Yeah,
explicit? What are those?
implicit solver, you have that Thomas algorithm. PDMA is a implicit solver,
Oh, अच्छा,
and
okay,
explicit
that
is
means.
like point Gauss Seidel, line Gauss Seidel.
Oh, okay, okay, that I understand. Now those boundary condition in the next slide.
Which one? Next slide. Correct.
Oh, sorry, next lecture. Okay, here uh, first thing we consider this value of psi is equals to 0 because it is kind of initial condition, whatever may we can give.
Yeah, you can take 501 as well instead of 0. It doesn't matter.
Okay, so this up to this point I like understood, but in the next slide when vorticity is considered, yeah, here I don't understand if you can explain it like.
Yeah, so let's say for this left wall, where I have q equal to 0, I know that
Hmm,
dou psi dou y is 0. So therefore, the second derivative would also be 0.
okay,
Now, so from my original equation, this one, omega equal to minus 4. So here I'm
yeah,
removing the dou 2 psi dou y square and
okay,
only keeping the second derivative of x. Then I'm
okay,
expanding or discretizing that derivative. And in that
hmm,
derivative, I don't know what psi 0 comma j is because that is outside the domain. How
okay,
to find that? To find that, I do some mathematical geometry once again. I know that v equal to 0 on that wall as well. So
hmm,
dou psi dou x has to be 0. Now dou psi dou x, I'm finding out at I equal to 1 using a central difference, telling that psi 2 minus psi 0 by 2 delta x would be 10. This is how I connect dou psi 0 to, this is how I connect psi 0 to psi 2 and replace it.
hmm. Okay, understood.
It's just math.
Understood. Okay. Yeah, it's yeah. Actually, it's only maths only. Okay. Yeah, thank you very much. These are all doubts. There's one doubt which is a little bigger doubt, which I ask you maybe in the next session.
Okay.
So, yeah, it is very general doubt, not related to. Okay. Thank you very
Okay,
much.
cool. Thank you then. Bye. Good night. See you next week.
Bye. Thank you.